Welcome to Sleepy Physicist, where we explore the gentle mysteries of the universe. Tonight, we're venturing into one of the most thought-provoking frontiers of physics, a realm so small and strange that it challenges everything we think we know about reality itself. Picture this: there exists a length so impossibly tiny that at its scale, the very concepts of space, time, and measurement begin to dissolve into something unrecognizable. This isn't science fiction. This is the Planck length, approximately 10 to the negative 35th meters, where the familiar laws of physics don't just bend, they may no longer apply in ways we currently understand. And here's what invites deep reflection. Nobody, not even our most brilliant physicists, truly understands what happens there. Before we drift deeper into this cosmic mystery, I'd love to know where you're listening from tonight. Are you tucked into bed in a quiet corner of Tokyo, watching the rain trace patterns on your window? Perhaps you're curled up on a couch in Manchester, nursing a warm cup of tea as the evening settles around you. Wherever you find yourself, I hope you're comfortable, because we're about to embark on a journey to the very edge of human understanding. If you enjoy these explorations of the universe's hidden corners, a gentle like and subscribe helps this channel reach others who find wonder in the unknown. And to those of you who've been following along on these nocturnal adventures, thank you for making this little community of curious souls possible. Now settle in as we descend through the layers of reality, past atoms, past subatomic particles, past everything we can directly observe, to a place where the universe might be far stranger and more deeply counterintuitive than we ever imagined. What exactly is the Planck length? To understand its significance, we need to appreciate just how unimaginably small it really is. If you took a single proton, that tiny nucleus at the heart of every hydrogen atom, and magnified it to the size of our entire observable universe, the Planck length would still be smaller than a grain of sand in comparison. It represents not just a measurement, but a fundamental boundary, a cosmic speed bump, where our understanding of reality hits a wall so absolute that many physicists wonder if distance itself has any meaning beyond it. This extraordinary scale emerged from the work of Max Planck in 1899, long before quantum mechanics had fully flowered into the strange and beautiful theory we know today. Planck was attempting to solve a seemingly simple problem about how heated objects emit light, but his solution required introducing a new constant into physics, now known as Planck's constant. When this constant is combined with the speed of light and Newton's gravitational constant, something remarkable emerges, a set of natural units that seem to represent the fundamental scales at which the universe operates. The Planck length isn't arbitrary. It's built into the very fabric of reality itself, emerging naturally from the most fundamental constants of nature. At this scale, quantum effects and gravitational effects become equally important, creating what physicists call the quantum gravity regime. Here's where things become particularly challenging. We have no tested theory that can describe what happens in this regime. Think about that for a moment. Throughout human history, we've pushed the boundaries of the very small. We've peered inside atoms, discovered quarks and leptons, mapped the quantum world with extraordinary precision. But at the Planck scale, our most successful theories simply reach their limits. General relativity, which beautifully describes gravity and the large-scale structure of spacetime, assumes that space and time are smooth and continuous. Quantum mechanics, which governs the behavior of particles and fields, treats space and time as a fixed background stage upon which quantum dramas unfold. But what happens when these two towering achievements of human thought are forced to confront each other? What occurs when the smooth space-time of Einstein meets the inherent uncertainty of quantum mechanics at the Planck scale? The honest answer is that we simply don't know. And this uncertainty points to something profound and deeply humbling about the nature of reality itself. As you listen to these words, perhaps feeling the soft weight of blankets around you or the gentle rhythm of your own breathing, consider this: the space around you, the very air you breathe, might not be the smooth, continuous medium it appears to be. At the smallest scales, some theories suggest that space-time itself becomes grainy, choppy, uncertain. This isn't merely a limitation of our instruments or our mathematics. This might be a fundamental feature of reality, a cosmic graininess that underlies everything we experience as solid and continuous. John Wheeler, the physicist who coined the term black hole, proposed in 1955 that at the Planck scale, space-time itself might be subject to quantum fluctuations. He called this theoretical phenomenon quantum foam, envisioning the fabric of reality as resembling a turbulent sea when viewed at sufficient magnification. Picture the surface of an ocean. From an airplane, it appears smooth and blue, an unbroken expanse stretching to the horizon, but descend closer, and you begin to see waves, white caps, the constant motion of water molecules dancing with each other in patterns both chaotic and beautiful. Wheeler suggested that space-time might behave similarly. At everyday scales, it appears perfectly smooth, a reliable stage upon which the universe performs its elaborate dance. But zoom in far enough, past atoms, past quarks, past anything we can directly observe, and space-time itself might begin to foam and bubble like a cosmic champagne, with virtual particles popping into existence and annihilating each other in time frames so brief that they make a hummingbird's wing beat seem like a geological epoch. This quantum foam, if it exists, represents something far more radical than merely very small structures in space. It suggests that space and time themselves, the most fundamental aspects of our reality, might not be fundamental at all. They might be emergent properties like wetness emerging from water molecules or consciousness arising from neural activity. At the deepest level, reality might be something else entirely, something our evolved brains and everyday experience give us no capacity to imagine. But here's where the deeper unease begins to surface. The quantum foam isn't just a theoretical curiosity. If it's real, it means that at every moment, in every cubic centimetre of space around you, reality is constantly fluctuating at scales far beyond direct perception. The solid table supporting your evening tea, the floor beneath your feet, the very atoms that compose your body, all of it might be resting upon layers of quantum uncertainty so profound that the concepts of here and there begin to blur. Some interpretations suggest that these quantum fluctuations aren't just mathematical abstractions, but represent physical processes at extremely small scales. Virtual particles, those ghostly entities that appear and disappear faster than light can travel between them, might be constantly creating and dissolving minute black holes at the Planck scale. These microscopic black holes would form, evaporate through Hawking radiation, and vanish in timescales measured in Planck time units, each lasting about 10 to the negative 44th seconds. Imagine, if you will, that reality at its deepest level resembles a cosmic storm, with black holes no larger than the Planck length constantly forming and evaporating in a dance of creation and dissolution so rapid and so small that it makes the quantum world we already struggle to understand seem comparatively slow and large scale. This isn't merely strange, it's a vision of reality that challenges our most basic assumptions about existence itself. The measurement problem becomes even more profound at these scales. In quantum mechanics, we're accustomed to the idea that observing a system affects its behavior, that measurement plays a fundamental role in determining outcomes. But at the Planck scale, the very act of trying to measure something becomes physically impossible in principle. To probe distances as small as the Planck length, you would need particles with such enormous energy that they would immediately collapse into black holes, destroying both the measuring device and the thing being measured. This creates a fundamental epistemological barrier. There may be aspects of reality that are not just currently unknown to us, but fundamentally resistant to direct observation. The Planck scale might represent a cosmic horizon beyond which direct measurement becomes impossible. We find ourselves in the strange position of being able to calculate this boundary with extraordinary precision while remaining unable to directly explore what lies beyond it. Take a moment to breathe deeply and consider what this might mean for your own experience of reality. Every sensation, every thought, every moment of consciousness you've ever experienced has emerged from processes that ultimately depend on the behavior of matter and energy at these incomprehensibly small scales. If reality becomes fundamentally uncertain at the Planck scale, what does that say about the nature of your own existence? The cosmological constant problem adds another layer of mystery to this already bewildering picture. When physicists attempt to calculate the energy density of empty space using quantum field theory, they encounter what's been called the worst theoretical prediction in the history of physics. The calculated value differs from observed reality by anywhere from 50 to 120 orders of magnitude. This isn't just a small error, it's a discrepancy so enormous that it suggests our understanding of the vacuum of empty space itself is fundamentally incomplete. This vacuum energy, if it existed at the levels predicted by our theories, would have torn the universe apart long before the first stars could form. The fact that we exist at all suggests that something profound is happening at the quantum level that we simply don't understand. Some theories propose that this energy is somehow moderated by unknown mechanisms operating at the Planck scale. Others suggest that our entire approach to understanding vacuum energy may need revision. The implications ripple outward like waves from a stone dropped in still water. If we can't fully understand empty space, how can we claim to understand anything? The vacuum surrounds us, fills us, comprises the vast majority of every atom in our bodies. If it harbours secrets we cannot fathom, then we are literally immersed in mystery, composed of mystery, thinking thoughts that emerge from processes we cannot yet comprehend. String theory and loop quantum gravity represent our most ambitious attempts to peer beyond the Planck scale veil, but both remain speculative, untested, and in many ways more philosophical than experimental. String theory suggests that the fundamental constituents of reality are not point particles, but tiny vibrating strings, so small that they would be invisible even at the Planck scale. These strings vibrate in higher dimensional spaces we cannot perceive, creating what we experience as different particles through their various vibrational modes. Loop quantum gravity takes a different approach, proposing that space and time themselves are not continuous but are composed of discrete units, quantum building blocks of reality comparable to the Planck length. In this view, space resembles a cosmic fabric woven from loops of spacetime, each stitch in the weave representing a fundamental unit of area or volume. Both theories remain unproven, perhaps untestable with current technology. They exist in the realm of mathematical possibility rather than experimental fact. This leaves us in the peculiar position of having our most advanced theories of reality remain beyond direct experimental confirmation, at least with any conceivable technology. Recent research has even challenged the assumption that physics necessarily breaks down at the Planck scale. Some physicists argue that the confidence with which we assert that new physics must emerge at these scales is not fully justified by the evidence. This uncertainty about our uncertainty adds yet another layer of mystery to an already complex situation. We find ourselves confronting the possibility that reality, at its deepest level, might remain beyond complete human comprehension. Not because we lack cleverness or technological sophistication, but because the very nature of reality at the Planck scale might be fundamentally incompatible with the kinds of direct knowledge that conscious beings like ourselves can possess. As the evening settles around you and your thoughts begin to soften at the edges, consider this. You are not separate from these mysteries. You are made of the same quantum fields that foam and fluctuate at the Planck scale. The uncertainty that pervades the deepest levels of reality flows through every atom of your being. In a very real sense, you are a temporary pattern in the cosmic foam, a brief organization of quantum uncertainty that has somehow learned to contemplate its own mysterious origins. This isn't meant to diminish your significance, but to expand it. You are not just a witness to these cosmic mysteries, you are part of them, woven into the very fabric of space-time that becomes so strange and uncertain at its smallest scales. Your thoughts, your dreams, your quiet moments of wonder, as you listen to these words, all of it emerges from processes that ultimately touch the deepest mysteries of existence. The unease of the Planck scale isn't just intellectual, it's existential. It invites us to confront the possibility that reality is far stranger, far more uncertain, and far more mysterious than our evolved minds are equipped to fully comprehend. We are pattern-seeking creatures living in a universe where the deepest patterns might remain beyond our grasp. And yet there's something beautiful in this uncertainty, something almost meditative in accepting that the universe holds secrets we may never unlock. Perhaps the real wisdom lies not in solving the mystery of the Planck scale, but in learning to live peacefully with the knowledge that such mysteries exist, that reality is deeper and stranger than we can imagine, deeper and stranger than we can imagine. But perhaps the most thought-provoking aspect of our Planck scale predicament isn't what we don't know, but what this ignorance reveals about the nature of knowledge itself. As you settle deeper into your evening routine, perhaps adjusting your pillow or pulling a blanket closer, consider this reflective thought. There may be fundamental limits to what conscious minds like ours can ever fully understand about reality. The trans-Planckian problem in cosmology adds another dimension to this epistemological challenge. If our universe underwent cosmic inflation, that rapid expansion in its earliest moments, then the quantum fluctuations we observe in the cosmic microwave background today may have originated from scales smaller than the Planck length. This creates a paradox that strikes at the heart of our scientific method. We're using observations of the largest scales in the universe to infer the behaviour of the smallest, but our theories suggest that information from sub-Planckian scales should be fundamentally inaccessible. It's as if we're trying to read a book where the most important chapters have been written in an alphabet that doesn't just use different symbols, but operates according to logical rules that our minds cannot process. The universe may be telling us a story about its own origins, but we may lack the cognitive architecture to fully comprehend the narrative. This brings us face to face with what philosophers call the hard problem of measurement at quantum scales. In our everyday experience, measurements seem straightforward. You place a ruler against an object, read the numbers, and you know its length. But at the Planck scale, the very act of measurement becomes paradoxical. To probe such tiny distances, you need photons with enormous energy, but concentrate that much energy in such a small space, and according to our understanding of gravity, you create a black hole. The measuring device destroys what it attempts to measure, consuming both observer and observed in a microscopic gravitational collapse that lasts for mere Planck time units. It's not just that we lack sufficiently precise instruments. The universe itself seems to have built-in mechanisms that prevent us from directly observing its deepest structures. Reality appears to have developed its own privacy settings, natural limits that hide its most fundamental operations behind barriers that may be insurmountable in principle. Some interpretations suggest that this isn't a bug in the universe's operating system, but a feature. Perhaps reality has evolved these protective mechanisms precisely because direct observation of Planck-scale processes would be incompatible with the existence of stable structures like atoms, molecules, and ultimately, observers like ourselves. We may live in a universe that can only support consciousness by keeping its deepest secrets hidden from direct examination. The Wheeler-DeWitt equation, which attempts to describe quantum gravity mathematically, reveals another deeply counterintuitive aspect of our predicament. When physicists try to combine quantum mechanics with general relativity at the most fundamental level, they encounter what's called the problem of time. Time, that most basic dimension of human experience, appears to vanish entirely from the equations that govern the deepest level of reality. This isn't simply a mathematical curiosity. It suggests that our experience of flowing time, of moments following one another in sequence, of cause preceding effect, may be an emergent feature that appears only at larger scales. At the Planck scale, some interpretations suggest the very concept of temporal flow becomes difficult to define. Past, present, and future may be constructs that have no direct counterpart in the fundamental structure of reality. Imagine trying to explain the concept of melody to someone who can only perceive individual, isolated musical notes with no sense of their temporal relationship. That may be analogous to our situation when we try to understand Planck-scale physics using concepts developed for a world where time flows in a single direction and events unfold in sequence. The implications ripple through every aspect of human experience. Every memory you've ever formed, every plan you've ever made, every moment of anticipation or regret, all of these mental phenomena depend on the assumption that time flows from past to future. But if time itself is merely an emergent property that breaks down at the Planck scale, what does that say about the nature of consciousness, memory, and identity? As you breathe quietly in whatever corner of the world you found yourself tonight, notice how each breath seems to follow the last in a natural sequence. This experience of temporal flow feels so fundamental, so undeniable, that it's difficult to imagine it could be anything other than a basic feature of reality. Yet physics is suggesting that this flow might be an effective approximation rather than an absolute feature of the universe, much like the apparent solidity of the chair you're sitting in. Loop quantum gravity attempts to address some of these paradoxes by proposing that space and time themselves are quantized, composed of discrete units rather than forming a smooth continuum. In this view, space-time resembles a vast cosmic fabric, woven from loops so small that they exist below the Planck scale. Each loop represents a fundamental quantum of area or volume, and the intricate way these loops connect and interact gives rise to the smooth spacetime we experience at larger scales. This theory suggests that if you could somehow zoom in far enough, space would begin to look grainy, pixelated like a digital photograph examined under extreme magnification. The smooth curves of Einstein's spacetime would reveal themselves to be composed of discrete building blocks, quantum stitches in the cosmic weave. But even this attempt to quantize spacetime leads to deeply challenging questions. If space and time are composed of discrete units, what lies between these units? What connects one quantum of space to the next? The theory attempts to answer these questions through the mathematics of spin networks and spin foams. But these mathematical structures exist in a realm so far removed from everyday experience that they might as well describe the architecture of dreams. String theory offers an even more radical reimagining of fundamental reality. According to this framework, the particles we think of as basic constituents of matter are actually vibrations of one-dimensional strings existing in dimensions we cannot perceive. These strings are so small that they would be invisible even if we could somehow observe phenomena at the Planck scale. They vibrate in a space with as many as 11 dimensions, most of which are curled up so tightly that they remain hidden from our three-dimensional perspective. The mathematics of string theory is breathtakingly elegant, suggesting deep connections between seemingly unrelated areas of physics and mathematics. But this elegance comes at a cost. String theory makes predictions about phenomena that may be beyond direct experimental verification. We find ourselves in the peculiar position of having our most advanced theories of fundamental reality be difficult to test empirically, at least with any conceivable technology. This raises profound questions about the nature of scientific knowledge itself. Science has always progressed through the interplay between theory and experiment, with observations serving as the final arbiter of theoretical disputes. But what happens when our theories venture into realms that may be permanently inaccessible to direct observation? Do we abandon the scientific method, or do we develop new ways of evaluating truth that don't depend solely on empirical verification? Recent developments in quantum field theory have revealed additional layers of complexity in our understanding of the vacuum. What we once thought of as empty space turns out to be seething with activity. Virtual particles constantly pop into existence and annihilate each other in processes that occur far below the threshold of direct observation. These quantum fluctuations aren't merely mathematical artifacts. They have measurable effects on the behavior of real particles and the structure of atoms. The Casimir effect demonstrates that these virtual particles can exert real forces. When two metal plates are placed extremely close together in a vacuum, they experience an attractive force due to the suppression of certain quantum fluctuations between them. It's as if empty space itself is pushing the plates together, revealing that the vacuum is anything but empty. But when physicists attempt to calculate the total energy density of these quantum fluctuations, they encounter the cosmological constant problem we mentioned earlier. The calculated value is so enormous that it would prevent the formation of any stable structures in the universe. The fact that we exist suggests that something profound is happening at the quantum level that we simply don't understand. Some theorists propose that the solution lies in the multiverse hypothesis. Perhaps our universe is just one bubble in an infinite foam of universes, each with its own values for fundamental constants. In this view, we observe the particular properties of our universe, not because they're somehow special or inevitable, but because we couldn't possibly find ourselves in a universe with different properties. Observers can only exist in universes compatible with the existence of observers. This anthropic reasoning provides a potential solution to the cosmological constant problem, but it comes with its own philosophically challenging implications. It suggests that many of the properties of our universe that seem fine-tuned for the existence of life may arise as statistical outcomes within a vast ensemble of possible realities. We are not necessarily the product of design or necessity, but one realization among many possible cosmic configurations. The multiverse hypothesis also raises questions about the nature of probability and existence. If infinite universes exist with every possible variation of physical laws and initial conditions, then every possible version of your life, every choice you didn't make, every path you didn't take, may be explored across a broader landscape of possibilities described by certain theoretical models. This isn't merely philosophical speculation. Some interpretations of quantum mechanics, particularly the many worlds interpretation, suggest that quantum measurements don't just reveal pre-existing properties of particles, but describe a branching structure of outcomes, each corresponding to a different measurement result. Every quantum event, from the decay of a radioactive atom to the firing of a neuron in your brain, can be described mathematically as contributing to this branching framework. If you've been following along with these gentle explorations of cosmic mysteries, you might find it comforting to know that members of our community get access to these episodes 48 hours early, completely ad-free, allowing for uninterrupted contemplation of these deep questions. You can join them whenever you feel ready, but for now, let's continue our descent into the quantum abyss. The many worlds interpretation suggests that as you listen to these words, countless other versions of yourself could be mathematically described as having slightly different experiences. In some branches, you decided to listen to music instead. In others, you chose a different podcast entirely. In still others, the quantum processes in your brain unfolded in ways that led to different thoughts, different emotional responses, different patterns of attention and reflection. This multiplicity of selves raises profound questions about identity and consciousness. If many versions of you are described across such theoretical frameworks, which one feels subjectively real? What makes your particular stream of consciousness meaningful compared to all the others? These questions venture into territory where physics and philosophy become deeply intertwined. The holographic principle adds yet another layer of strangeness to our picture of fundamental reality. This idea, emerging from black hole thermodynamics and string theory, suggests that all the information contained in a volume of space can be encoded on its two-dimensional boundary. Just as a hologram stores three-dimensional information on a flat surface, the universe itself might be described using a holographic framework, with complex behavior emerging from information encoded on a distant boundary. If the holographic principle is correct, then the three-dimensional space you're sitting in right now may be describable as an emergent projection from information stored on a two-dimensional surface at the edge of the observable universe. Your body, your thoughts, your entire reality might be patterns of information unfolding within this framework. This isn't merely a metaphor or a thought experiment. The holographic principle makes specific mathematical predictions and has found applications in areas ranging from condensed matter physics to quantum information theory. It suggests that the fundamental currency of reality might not be matter or energy, but information itself. The implications are staggering. If reality is fundamentally informational, then the hard problem of consciousness, the question of how subjective experience arises from physical processes, takes on new dimensions. Perhaps consciousness isn't something that emerges solely from complex arrangements of matter, but something more closely related to the information processing structures that appear to underlie physical reality. These ideas remain highly speculative, of course. They exist at the intersection of cutting-edge physics and philosophical inquiry, in a realm where mathematical elegance and conceptual depth sometimes extend beyond direct experimental confirmation. But they point toward a view of reality that is far stranger and more mysterious than anything our ancestors could have imagined. The quantum Zeno effect reveals another way in which consciousness and quantum mechanics might be connected, though we must be careful not to overstate these connections. This phenomenon demonstrates that frequent measurements of a quantum system can actually prevent it from evolving, freezing it in its initial state through the very act of observation. It's as if watching a quantum pot prevents it from boiling. While this effect has been demonstrated in laboratory settings with sophisticated measurement devices, some speculative interpretations suggest that consciousness itself might play a role in quantum measurement. This remains highly controversial and lacks scientific consensus, but it raises intriguing questions about the relationship between mind and physical reality. The delayed choice quantum eraser experiments reveal even more counterintuitive aspects of quantum reality. These experiments suggest that decisions made about how to measure a quantum system can be correlated with outcomes in ways that challenge classical intuitions about time and causality, even when the measurement choice occurs after the system has been detected. These experiments don't prove that consciousness can directly influence quantum events, but they do suggest that the relationship between measurement, information, and physical reality is far more complex and subtle than we typically assume. They point toward a universe where the boundaries between observer and observed, between mind and matter, might be more fluid than our everyday experience suggests. As the night deepens around you, and these ideas begin to settle into the quiet spaces of your mind, consider what it means to be a conscious observer in such a strange and uncertain universe. You are not separate from these quantum mysteries. You are intimately connected to them. The atoms that compose your body were forged in the hearts of ancient stars through processes that depend on quantum mechanics. The neurons firing in your brain as you contemplate these ideas operate according to principles that ultimately trace back to the same quantum realm we've been exploring. The uncertainty that pervades the Planck scale flows through every aspect of your existence. Your thoughts emerge from quantum processes in your brain. Your memories are stored in molecular configurations that depend on quantum chemistry. Even your sense of self, your feeling of being a continuous unified consciousness, might be an emergent property arising from the complex interplay of quantum systems. This isn't meant to reduce you to mere quantum mechanics, but to expand your sense of connection to the deepest mysteries of existence. You are not just a witness to cosmic uncertainty. You are a temporary focal point of that uncertainty, a brief organization of quantum possibilities that has somehow learned to contemplate its own mysterious nature. The anthropic principle suggests that the universe must have properties compatible with the existence of observers, since observers are here to observe it. But this raises the question of whether consciousness plays a more fundamental role in shaping reality than we typically assume. Some interpretations suggest that the universe might require observers not just to witness its evolution, but to participate indirectly in defining the conditions under which physical structures become observable? This remains highly speculative, and we must be careful not to overstate the role of consciousness in quantum mechanics. But it does suggest that the relationship between mind and physical reality might be more intimate and mysterious than the classical scientific worldview suggests. We might not be separate from the universe we study, but deeply embedded within the processes that give rise to it. The measurement problem in quantum mechanics reveals the deep strangeness of this observer-involved universe. Before measurement, quantum systems exist in superpositions of multiple possible states. The act of measurement causes this superposition to resolve into a single, definite outcome. But what constitutes a measurement? Where exactly does the boundary lie between the quantum realm of multiple possibilities and the classical realm of definite outcomes? These questions have puzzled physicists for nearly a century, and they touch on fundamental issues about the nature of reality and consciousness. Some interpretations suggest that consciousness itself plays a special role in collapsing quantum superpositions, though this remains controversial and lacks scientific consensus. Other interpretations propose that the boundary between quantum and classical is more gradual and context-dependent than we typically assume. The decoherence theory offers a more prosaic explanation, suggesting that quantum superpositions lose coherence when systems become entangled with their environment. In this view, measurement doesn't require consciousness, just interaction with a sufficiently complex environment. But this raises new questions about what constitutes sufficient complexity and whether consciousness might represent a particularly rich form of environmental interaction. As we approach the end of our journey through these quantum mysteries, it's worth reflecting on what we've discovered about the limits of human knowledge and understanding. The Planck scale represents not just a physical boundary, but an epistemological one, a limit to what conscious beings like ourselves might ever be able to know directly about the fundamental nature of reality. This isn't necessarily a cause for despair. There's something beautiful and humbling about acknowledging that the universe is deeper and stranger than we can fully comprehend. It reminds us that wonder and mystery are not obstacles to overcome, but essential features of existence itself. Perhaps the unease of the Planck scale isn't that it reveals the limits of human knowledge, but that it invites us to confront the possibility that reality is far more magnificent and mysterious than we ever dared imagine. We are finite beings in an infinite universe, temporary patterns of organization trying to understand permanence, quantum creatures attempting to grasp classical certainty. If you found yourself drawn to these explorations of the deepest mysteries of existence, you might enjoy our previous journey into how the fabric of space-time itself might be an illusion. In our episode titled Space-Time Fabric Just Shattered, Reality is an Illusion. There we explored how the smooth continuum of Einstein's universe gives way to something far stranger at the quantum level. For now, as you prepare to drift into sleep or simply sit quietly with these profound uncertainties, remember that you are not alone in this vast and mysterious cosmos. You are part of the universe's attempt to understand itself, a temporary focal point of cosmic awareness in an ocean of quantum possibility. The uncertainty that once felt overwhelming at the Planck scale also gives rise to everything we find beautiful and meaningful in existence, including the capacity to contemplate these very mysteries. Sleep well, fellow travellers in the quantum foam, and remember that sometimes the most profound wisdom lies not in finding answers, but in learning to be comfortable with the most beautiful questions. Perhaps most conceptually challenging is how our ignorance at the Planck scale calls into question the very nature of existence itself. When physicists attempt to understand what happens during the earliest moments after the Big Bang, they encounter what's known as the Planck epoch, a period lasting from time 0 to approximately 10 to the negative 43rd seconds. During this briefest of moments, the universe was so hot, so dense and so energetic that all our known laws of physics simply ceased to apply. Picture this if you can. Everything that would eventually become the observable universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, all of it compressed into a region smaller than a proton. At such densities, the distinction between matter and space-time itself becomes meaningless. Gravity, electromagnetism, and the nuclear forces merge into a single, unified interaction that we have no mathematical framework to describe. This isn't merely a technical limitation of our current theories. It represents a fundamental barrier to understanding the origins of everything we know and are. The universe emerged from conditions so extreme that they may have operated according to physical principles entirely alien to anything we can observe or measure today. We are, in a very real sense, cut off from our own cosmic birth certificate. The inflationary model of cosmology attempts to address some of these mysteries by proposing that the early universe underwent a period of exponential expansion, stretching space itself at rates far exceeding the speed of light. During this inflationary epoch, quantum fluctuations that began at scales smaller than the Planck length were stretched to cosmic proportions, eventually becoming the seeds from which galaxies and large-scale structures would grow. But here's where the paradox deepens. If inflation did stretch sub-Planckian fluctuations to observable scales, then the patterns we see in the cosmic microwave background today carry information from realms that our theories tell us should be fundamentally inaccessible. It's as if the universe is showing us photographs of places we can never visit, speaking to us in a language we can never fully comprehend. This creates what cosmologists call the trans-Planckian problem. How can we trust our theories about the early universe if they depend on physics from scales where those very theories break down? It's like trying to understand a symphony by analysing the silence that came before the first note, except that silence might have been filled with music, played in frequencies our ears could never detect. Take a moment to consider how this uncertainty pervades every aspect of cosmological understanding. When astronomers look out into space and back in time, observing galaxies that formed billions of years ago, they're seeing structures that ultimately trace their origins to processes that may be beyond complete human comprehension. The spiral arms of distant galaxies, the clustering of galactic superclusters, even the very atoms that compose your body tonight. All of these emerged from quantum seeds planted in a realm of physics that defies everyday intuition. Some interpretations of string theory suggest that our universe might be what's called a brane, a multi-dimensional membrane floating in an even higher dimensional space, called the bulk. In this picture, the Planck scale might represent not just a limit to measurement, but an interface between our familiar three-dimensional reality and realms with different numbers of spatial dimensions entirely. Imagine trying to explain the concept of depth to beings who can only perceive length and width. That might be analogous to our situation when we attempt to understand how extra dimensions could be compactified at the Planck scale, curled up so tightly that they remain invisible even in principle. These hidden dimensions might be all around us, permeating every cubic centimetre of space, yet remaining as inaccessible as regions we can never directly observe. The mathematical structures required to describe these extra dimensions are so abstract that they exist in a realm of pure thought, disconnected from anything we could ever hope to observe directly. We find ourselves in the strange position of using human intuition, evolved to navigate a three-dimensional world of medium-sized objects, to contemplate realities that might involve 6 or 7 additional spatial dimensions operating according to geometries that have no analogue in everyday experience. Loop quantum gravity offers a different but equally conceptually challenging vision of Planck scale reality. This theory suggests that space and time are not continuous, but are instead woven from discrete quantum threads, loops of space-time so small that they exist below the Planck length. These loops form networks that connect and interact in ways that give rise to the smooth space-time we experience at larger scales. But what exists between these loops? If space is quantized, composed of discrete units, like pixels in a cosmic digital photograph, what lies in the gaps between pixels? The theory attempts to address these questions through mathematical frameworks involving spin networks and spin foams, but these abstractions push the boundaries of human conceptual capacity. Consider the implications for your own existence. Every thought you think, every breath you take, every heartbeat that sustains your life depends on processes that ultimately trace back to the behavior of these theoretical quantum loops. If space itself is granular rather than smooth, then your consciousness emerges from discrete quantum events occurring in a pixelated universe where the very concept of continuous motion might be a perceptual approximation shaped by the limits of human awareness. The emergence of classical space-time from quantum loops remains one of the deepest mysteries in theoretical physics. How does something as fundamental as the smooth flow of time emerge from discrete quantum interactions? It's like asking how the continuous melody of a symphony emerges from individual notes, except that in this case, the notes themselves might be playing in dimensions we cannot perceive, following rhythms that exist below the threshold of temporal resolution. Recent developments in quantum information theory have revealed another deeply intriguing aspect of Planck scale physics. The ite from bit hypothesis, proposed by John Wheeler, suggests that reality might be fundamentally informational, that matter and energy are secondary manifestations of something more basic, the processing and storage of information at quantum scales. If this interpretation is correct, then the universe isn't made of stuff in any conventional sense. Instead, it's made of questions and answers, of bits of information encoded in quantum states and processed through quantum interactions. Your body, your thoughts, your memories, all of these would be patterns of information rather than arrangements of matter. The solid chair you're sitting in would be, at its deepest level, describable as a highly sophisticated physical system whose behaviour gives rise to the experience of solidity. This informational view of reality connects to the holographic principle we discussed earlier, but it pushes the implications even further. If reality is fundamentally computational, then consciousness might not be something that emerges solely from complex arrangements of matter, but something more closely related to the information processing structures that underlie physical phenomena. The implications ripple through every aspect of human understanding. Free will, personal identity, the nature of consciousness itself, all of these concepts take on new meanings in a universe where information is primary and matter is secondary. Are your thoughts and decisions the result of classical neural computation, or do they emerge from multi-scale information processing occurring at levels where the conventional notion of causality becomes less clear. The quantum mind hypothesis remains highly controversial and lacks scientific consensus, but it raises profound questions about the relationship between consciousness and the fundamental structure of reality. Some interpretations suggest that quantum coherence in microtubules within neurons might allow the brain to perform quantum computations, while others propose that consciousness itself might be closely linked to the quantum measurement process. These ideas venture into territory where neuroscience, quantum physics, and philosophy of mind converge in ways that challenge our most basic assumptions about the nature of subjective experience. If quantum effects do play a role in consciousness, then the uncertainty that feels unsettling at the Planck scale might be intimately connected to the very phenomenon that allows us to contemplate that uncertainty. The delayed choice quantum eraser experiments reveal another way in which the normal rules of causality appear to behave differently in quantum systems. These experiments suggest that decisions about how to measure quantum particles can be correlated with outcomes in ways that challenge classical intuitions about time, even after interactions with detection apparatus have already occurred. While these experiments don't prove that consciousness can directly influence quantum events, they do reveal that the relationship between observation, measurement, and physical reality is far more nuanced than classical physics suggests. They point toward a universe where the boundaries between cause and effect, between observer and observed, might be more fluid than our everyday experience indicates. As you sit quietly listening to these words, notice how your own experience of time seems to flow smoothly from past to future. Each moment appears to follow the last in a natural sequence, creating the narrative thread of your conscious experience. Yet quantum mechanics suggests that this flowing river of time might be more like a series of discrete quantum snapshots, individual frames in a cosmic movie that collectively create the illusion of smooth motion. The problem of time in quantum gravity theories reveals just how fundamental this illusion might be. When physicists attempt to write down equations that combine quantum mechanics with general relativity, they often find that time disappears entirely from the most fundamental descriptions. The Wheeler-DeWitt equation, which represents one attempt to describe quantum gravity, contains no time parameter at all. This suggests that time as we experience it might be an emergent property, something that appears only at larger scales when quantum gravitational effects become negligible. At the Planck scale, some interpretations suggest there might be no meaningful distinction between past, present, and future. All moments might exist simultaneously within a timeless mathematical framework describing every possible configuration of matter and energy. The implications for human consciousness are profound. Every memory you've ever formed depends on the assumption that the past is fixed and the future is open. Every plan you've ever made assumes that cause precedes effect, that actions in the present can influence outcomes in the future. But if time itself is an approximation that breaks down at the deepest levels of reality, what does that say about the nature of personal identity, moral responsibility, or meaning itself? Some theories in quantum cosmology suggest that the entire universe might be describable as a quantum superposition of many possible histories. In this view, the Big Bang didn't happen once, but is represented across a vast landscape of possible cosmic evolutions. Our experience of a single, definite history would be one path through this larger mathematical structure, selected through quantum processes we do not yet fully understand. The anthropic principle adds another layer of mystery to this already complex picture. The fundamental constants of nature, from the strength of gravity to the mass of the electron appear to be finely balanced for the existence of stable atoms, stars, planets, and ultimately life itself. Change any of these constants slightly, and the universe becomes inhospitable to complex structures. Some interpretations suggest that this apparent fine-tuning may be explained by a multiverse, an ensemble of universes with different physical parameters. In this view, we observe the particular values we do not because they are inevitable, but because consciousness can only arise in universes compatible with its emergence. But this multiverse hypothesis raises its own deeply challenging questions. If many universes exist with a wide range of physical laws and initial conditions, then many possible versions of your life could be mathematically described within this broader framework. This vast landscape of possibilities might feel comforting to some, suggesting that every outcome exists somewhere. But it also implies that your particular stream of consciousness may not be unique in an absolute sense, even though it remains uniquely meaningful to you. The measure problem in cosmology attempts to address these questions by asking how probabilities should be assigned within such an expansive framework. If many universes exist, how do we meaningfully explain why we experience this one? The mathematics involved stretches conventional probability theory to its limits. Recent developments in eternal inflation theory suggest that this cosmic landscape might not only be vast in space, but persistent over time. In this picture, inflation continues in some regions indefinitely, constantly generating new regions of spacetime with differing physical properties. This idea invites profound reflection. If universe creation is an ongoing process, then structures like galaxies, stars, and even conscious observers might arise repeatedly across a vast cosmic backdrop. The philosophical idea of eternal return takes on new resonance here. If time extends indefinitely and physical configurations are finite, certain arrangements of matter could recur across cosmic history. This remains a theoretical possibility rather than an established fact. These ideas are not mere speculation detached from science, but extrapolations from mathematical frameworks that successfully describe many aspects of observed reality. When followed to their logical conclusions, they suggest a universe far richer and more expansive than human intuition alone could anticipate. As you breathe quietly in whatever corner of the world has become your sanctuary tonight, consider what it means to be a conscious observer within such an immense and recurring cosmos. Your thoughts, your experiences, your sense of being a particular individual may be both extraordinarily rare and deeply connected to universal processes. The quantum fluctuations that seeded galaxies also gave rise to the conditions necessary for stars, planets, chemistry, and eventually life. Every atom in your body was forged in ancient stars whose remnants scattered the elements across space. This cosmic continuity connects you directly to the deepest mysteries of the Planck scale. The quantum processes we cannot directly observe gave rise to the classical world that supports life and consciousness. You are not separate from these mysteries, but one of their most remarkable outcomes. The hard problem of consciousness, the question of how subjective experience arises from physical processes, takes on new dimensions when viewed through quantum theory. Some approaches suggest consciousness may be a fundamental feature of reality, while others see it as an emergent phenomenon arising from complex systems. Integrated information theory proposes that consciousness corresponds to the degree to which a system integrates information. Under this view, varying degrees of consciousness could exist across many physical systems. These ideas are both awe-inspiring and deeply challenging. They suggest that experience may be more widespread in nature than previously assumed, though such interpretations remain speculative. This panpsychist perspective lacks scientific consensus, but it highlights the possibility that mind and matter are not fundamentally separate, but intertwined aspects of a deeper underlying reality. The measurement problem in quantum mechanics illustrates the difficulty of drawing sharp boundaries between observer and observed. Every measurement involves interaction, yet where the quantum world gives way to classical experience remains unclear. Some interpretations suggest consciousness may play a role in this transition, though this idea remains controversial. Others emphasize environmental interaction and decoherence. The delayed choice experiments reinforce how subtle and counterintuitive these boundaries can be, challenging classical assumptions about causality without violating known physical laws. These puzzles may feel abstract, but they influence how we think about reality, identity, and knowledge itself. If the universe is fundamentally quantum, then much of what we experience may be emergent rather than fundamental. Decoherence helps explain why classical behavior appears, but it doesn't explain how specific outcomes are selected. That mystery remains open. Some physicists argue that this gap reflects a transition between descriptive levels rather than a flaw in theory. Reality may be layered, with each level governed by its own principles. The global workspace theory suggests consciousness arises when information becomes widely accessible across brain systems. While neural processing is largely classical, its molecular foundations remain quantum. The question of whether quantum effects influence consciousness directly remains unresolved. The Or-Core theory represents one attempt to bridge this gap, though it remains debated. Regardless of the mechanism, the fact that matter can give rise to awareness remains one of the most extraordinary features of the universe. As these ideas settle into your awareness, consider the mystery of your own existence. You are a temporary organization of quantum fields capable of reflection and wonder. The atoms that compose you were forged in stars long ago, and one day they will return to the cosmic cycle, becoming part of future worlds and perhaps future minds, contemplating the same questions. The uncertainty that can feel deeply unsettling at the Planck scale is the same uncertainty that makes your existence possible. Without quantum indeterminacy, the universe would be a static, unchanging crystal of perfect order. It is precisely because reality is fundamentally uncertain, because the future is not completely determined by the past, that evolution, growth, creativity, and consciousness become possible. In a very real sense, you are the universe becoming conscious of itself, a temporary focal point of cosmic awareness that emerged from the quantum foam and will eventually return to it. But in the brief span between emergence and dissolution, you have the remarkable opportunity to contemplate these deepest mysteries of existence, to participate in the universe's ongoing project of self-understanding. The questions we've explored tonight about the Planck scale, quantum mechanics, and consciousness might never be fully answered. They represent the growing edge of human knowledge, the frontier where scientific understanding meets the fundamental mystery of existence itself. But perhaps the real value lies not in finding final answers, but in learning to live peacefully with profound uncertainty, to find meaning and beauty in the questions themselves. If you found yourself drawn to these explorations of the deepest mysteries of reality, you might be interested in our previous journey into how the very fabric of space-time might be an illusion. In that episode, titled Spacetime Fabric Just Shattered, Reality is an Illusion, we explored how Einstein's smooth continuum gives way to something far stranger and more fundamental at the quantum level, revealing connections between consciousness, information, and the nature of existence that invite us to rethink everything we thought we knew about reality itself. For now, as you prepare to drift into sleep or simply sit quietly with these profound uncertainties, remember that you are not alone in this vast and mysterious cosmos. The same quantum fields that foam and fluctuate at the Planck scale flow through every aspect of your being, connecting you intimately to the deepest mysteries of existence. In contemplating these questions, you participated in the universe's ongoing attempt to understand itself, adding your own unique perspective to the cosmic conversation between mind and matter, between known and unknown, between the awe and wonder of being conscious in a quantum universe. Perhaps the most deeply thought-provoking aspect of our journey to the Planck scale is what it reveals about the nature of observation itself. As you settle deeper into whatever quiet space has become your sanctuary tonight, consider this challenging possibility. The very act of trying to understand reality at its deepest level might be fundamentally self-defeating. The observer effect in quantum mechanics, which we've touched upon throughout our exploration, becomes truly paradoxical when we attempt to apply it to Planck scale phenomena. To observe something at the Planck length, we would need to concentrate enormous amounts of energy into incredibly tiny regions of space. But according to our understanding of gravity, such energy concentrations would immediately collapse into microscopic black holes, preventing direct observation in a gravitational maelstrom that lasts mere Planck time units. This creates what some physicists call the ultimate measurement paradox. The universe appears to have evolved its own natural constraints, mechanisms that prevent direct observation of its most fundamental structures. It's as if reality has developed built-in limits against too much scrutiny, protecting its deepest secrets through the very laws of physics themselves. Take a moment to breathe deeply and consider what this means for the scientific method, that most reliable tool for understanding the natural world. Science has always progressed through the interplay between theory and observation, with experiments serving as the final arbiters of truth. But at the Planck scale, this method encounters what might be an extraordinary boundary, a cosmic firewall that separates the knowable from the unknowable. Some interpretations suggest that this barrier isn't accidental but essential. Perhaps consciousness and complex structures, like atoms, molecules, and life itself, can only exist in a universe where the deepest levels of reality remain hidden. If we could somehow observe Planck scale processes directly, the very act of observation might be incompatible with the existence of observers. This leads to a profound philosophical puzzle. We might live in a universe naturally structured to be partially incomprehensible to the conscious beings it produces. The mystery isn't a bug in the cosmic operating system, but a feature, a necessary condition for the emergence of anything complex enough to wonder about its own origins. Recent developments in quantum information theory have revealed another layer to this puzzle. The holographic principle suggests that all the information in a three-dimensional region of space might be encoded on its two-dimensional boundary, like a cosmic version of the holograms on credit cards that contain three-dimensional images in flat surfaces. If this principle applies to the universe as a whole, then everything you see around you, everything you are, might be understood as a projection from information stored on a distant boundary at the edge of the observable universe. Your thoughts, your memories, your sense of being a unique individual, all of these might be patterns playing out on a vast cosmic holographic screen. This isn't merely speculative mathematics. The holographic principle has found applications in understanding black holes, quantum field theory, and even condensed matter physics. It suggests that the fundamental currency of reality might not be matter or energy, but information itself, processed and stored in ways that transcend our ordinary understanding of space and time. The implications ripple through every aspect of human experience. If reality is fundamentally informational, then the hard problem of consciousness, the question of how subjective experience arises from objective physical processes, might require a significant reconceptualization. Perhaps consciousness isn't something that emerges from complex arrangements of matter, but something more fundamental, more closely related to the information processing that seems to underlie all physical phenomena. Consider the device you're using to listen to these words. Whether it's a phone, computer, or speaker, it operates by processing information, converting digital patterns into sound waves that travel through air to reach your ears. But according to the holographic principle, your brain might be doing something conceptually similar on a much grander scale, processing information encoded in the quantum structure of space-time itself to create the rich tapestry of conscious experience. The it from bit hypothesis, proposed by physicist John Wheeler, pushes this idea even further. Wheeler suggested that reality might be fundamentally made of questions and answers, of binary choices at the quantum level that accumulate into the complex structures we observe. In this view, matter and energy are secondary phenomena, shadows cast by more fundamental informational processes. If Wheeler was correct, then every quantum measurement, every collapse of a wave function, every moment when possibility becomes actuality, represents a fundamental informational event, a binary choice that adds one more bit of information to the universe's growing database of reality. You're not just made of atoms, you are made of answers to questions that were asked billions of years ago at the quantum level. This informational view connects to recent research in quantum biology, where scientists have discovered quantum effects in biological systems that were previously thought to be too warm and noisy to support quantum coherence. Photosynthesis in plants appears to use quantum superposition to find the most efficient pathways for energy transfer. Some birds might navigate using quantum entanglement in proteins in their eyes. Even the process of smell might involve quantum tunneling in receptor molecules. These discoveries suggest that life hasn't just adapted to live in a quantum universe. It has learned to make use of quantum effects for survival advantages. The boundary between quantum and classical isn't as sharp as we once thought. Instead, biology seems to dance along this boundary, using quantum effects when they're useful, while maintaining enough classical stability to support complex structures. This quantum biology research remains in its early stages, and we must be careful not to overstate the role of quantum effects in living systems. But it does suggest that the strange world of quantum mechanics isn't confined to sterile laboratory conditions. It's woven into the fabric of life itself, operating in the warm, wet, noisy environment of biological systems, where classical physics suggests quantum effects should be impossible. As you listen to these words, quantum processes might be occurring in the neurons of your brain, in the molecules that store your memories, in the proteins that regulate your breathing. The boundary between you and the quantum world isn't as clear as everyday experience suggests. You are not separate from these mysteries. You are intimately connected to them at the most fundamental level. The delayed choice quantum eraser experiments we discussed earlier reveal another deeply counterintuitive aspect of quantum reality. These experiments suggest that information about quantum systems can appear to influence outcomes in ways that challenge classical assumptions about causality and the flow of time even after detection has occurred. While these experiments don't prove that consciousness can directly influence quantum events, an idea without scientific consensus, they do reveal that the relationship between information, measurement, and physical reality is far more complex than classical physics suggests. They point toward a universe where the boundaries between observer and observed, between cause and effect, might be more fluid than our everyday experience indicates. Some interpretations of these experiments propose that reality might be retroactively determined, that the properties we measure today might depend on measurements that haven't been made yet. This doesn't violate special relativity because no information can be transmitted faster than light, but it does suggest that the universe might be far more interconnected and non-local than we typically assume. The implications for human consciousness are profoundly intriguing. If quantum correlations connect events across time, then the decisions you make today might somehow be connected to quantum events that occurred before you were born. The patterns of neural activity that constitute your thoughts might be linked through quantum correlations to events scattered across space and time in ways that transcend ordinary causality. This remains highly speculative, and we must emphasize that there is no scientific consensus on these interpretations, but they point toward a vision of reality that is far more mysterious and interconnected than the mechanical clockwork universe that classical physics once suggested. They invite us to consider the possibility that consciousness itself might be woven into the fabric of space-time in ways we're only beginning to glimpse. The anthropic principle adds another layer of mystery to these quantum puzzles. The fundamental constants of nature appear to be fine-tuned with extraordinary precision for the existence of stable atoms, stars, planets, and life. Change the strength of gravity by a tiny amount, and stars either burn out too quickly or never ignite at all. Alter the mass of the electron, and atoms become impossible. Adjust the nuclear forces, and the elements required for chemistry cannot form. This fine-tuning is so precise that it has led some physicists to propose the multiverse hypothesis, the idea that our universe is just one bubble in an infinite foam of universes, each with different values for the fundamental constants. In this view, we observe the particular values we do not because they're inevitable, but because we couldn't possibly find ourselves in a universe with different properties. But the multiverse hypothesis raises its own challenging questions. If infinite universes exist with every possible combination of physical laws, then every possible version of your life could be realized somewhere. Every choice you didn't make, every path you didn't take, every word you didn't speak, all of these alternatives might exist within this broader framework. This infinite multiplication of possibilities creates what philosophers call the measure problem. If everything that can happen does happen somewhere in the multiverse, how do we assign meaning or probability to any particular outcome? How do we explain why you find yourself in this particular universe, with this particular history, rather than any of the infinite alternatives? Some theories suggest that consciousness itself might play a role in selecting which branch of the multiverse we experience. This remains pure speculation without scientific support, but it points toward questions about the relationship between awareness and reality that push the boundaries of both physics and philosophy. The many worlds interpretation of quantum mechanics offers a related but distinct vision of multiple realities. According to this interpretation, every quantum measurement doesn't just reveal pre-existing properties, but describes branching outcomes, each corresponding to a different measurement result. Every quantum event, from the decay of a radioactive atom to the firing of a neuron in your brain, potentially corresponds to multiple possible histories. If this interpretation is correct, then as you listen to these words, countless other versions of experience could be described, each unfolding slightly differently. In some, you decided to listen to music instead. In others, you chose a different podcast entirely. In still others, the quantum processes in your brain unfolded differently, leading to different thoughts, different emotional responses, different patterns of attention and memory formation. This multiplicity of selves raises profound questions about personal identity and the nature of consciousness. If many versions of experience can be described across the quantum multiverse, what defines continuity of self? What makes your particular stream of consciousness meaningful? As these ideas percolate through your mind tonight, notice how they challenge your assumptions about the nature of reality and your place within it. The universe we've been exploring together is far stranger, far more uncertain, and far more mysterious than the solid, predictable world of everyday experience. Yet this strangeness might not be a flaw in the cosmic design, but its most beautiful feature. The uncertainty that can feel unsettling at the Planck scale is the same uncertainty that makes growth, change, and creativity possible. Without quantum indeterminacy, the universe would be a static crystal of perfect order. Beautiful perhaps, but incapable of generating the complexity required for stars, planets, life, or consciousness. It is precisely because the future is not completely determined by the past that evolution, learning, and wonder become possible. In contemplating these mysteries, you participate in the universe's ongoing attempt to understand itself. Every question you ask, every moment of wonder you experience, every connection you make between seemingly disparate ideas, all of these contribute to the cosmic conversation between mind and matter, between the known and the unknown. The quantum foam that bubbles at the Planck scale might seem impossibly remote from your daily experience, but it's intimately connected to everything you are and everything you do. The atoms that compose your body condensed from quantum fields that emerged from the Big Bang. The forces that hold those atoms together operate according to quantum mechanical principles. Even the thoughts you're thinking right now depend on quantum processes in the molecules that store and transmit information in your brain. You are not separate from the quantum world. You are a temporary organization of quantum fields that has somehow learned to contemplate its own mysterious nature. The uncertainty principles that govern the behavior of subatomic particles also govern the neural processes that give rise to consciousness, memory, and the capacity for wonder. This connection between the quantum and the conscious remains one of the deepest mysteries in science. Some researchers have proposed that quantum effects in microtubules within neurons might play a role in consciousness, though this theory remains controversial and lacks strong experimental support. Others suggest that consciousness might be an emergent property that arises from classical neural computation, with quantum effects playing only indirect roles. But regardless of the specific mechanisms, the fact remains that consciousness emerges from quantum mechanical systems. Your ability to understand these ideas, to feel wonder or confusion or awe, represents an extraordinary achievement of cosmic evolution. The universe has organized itself in such a way that parts of it can contemplate the whole, that quantum fields can arrange themselves into patterns capable of asking questions about quantum fields. The measurement problem in quantum mechanics reveals how mysterious this achievement really is. Before measurement, quantum systems exist in superpositions of multiple possible states. The act of measurement causes this superposition to collapse into a single, definite outcome. But what constitutes a measurement? Where exactly does the boundary lie between the quantum realm of multiple possibilities and the classical realm of definite outcomes? Some interpretations suggest that consciousness itself plays a special role in this process, though this remains speculative and lacks scientific consensus. Others propose that the boundary is more gradual and context-dependent, emerging through environmental decoherence rather than conscious observation. But the questions persist. How does the potential become actual? How do possibilities become realities? How does the quantum many become the classical one? These questions touch on fundamental issues about the nature of existence itself. If reality, at its deepest level, consists of probability waves and quantum superpositions, what does it mean for anything to be definitively real? How do we account for the apparent solidity and definiteness of our everyday experience? The decoherence theory offers a partial answer, suggesting that quantum systems lose their coherent superposition states when they interact with their environment. The larger and more complex a system becomes, the more quickly it decoheres, which explains why we don't observe quantum superpositions in everyday macroscopic objects, like chairs or cats. But decoherence doesn't solve the measurement problem completely. It explains how quantum coherence is lost, but not how specific outcomes are selected from the range of quantum possibilities. The process by which the wave function appears to collapse, by which one possibility out of many becomes actualized, remains one of the deepest mysteries in physics. Some physicists argue that this mystery might never be fully resolved because it involves a fundamental category error, an attempt to apply concepts developed for classical systems to quantum phenomena that operate according to entirely different principles. Just as it's impossible to explain the wetness of water purely in terms of individual H2O molecules, it might be impossible to explain the emergence of classical reality purely in terms of quantum mechanics. This suggests that reality might be fundamentally layered, with each level operating according to its own principles that cannot be reduced to lower levels. Consciousness might represent another such emergent level, arising from but not reducible to the neural processes that support it. The global workspace theory of consciousness proposes that awareness arises when information becomes globally accessible across different brain systems, creating a unified model of reality that can guide behavior and decision-making. This integration happens through neural networks that operate according to classical physics, but the information being integrated ultimately traces back to quantum processes at the molecular and atomic levels. The boundary between quantum and classical in the brain remains a subject of intense research and speculation. While most neuroscientists assume that neural computation is essentially classical, operating like a biological computer that processes information through electrical and chemical signals, some researchers have proposed that quantum effects might play important roles in consciousness, memory, or decision-making. These quantum theories of consciousness remain highly controversial and lack strong experimental support. The brain appears to be too warm, wet and noisy to support the kind of delicate quantum coherence that would be required for quantum computation. But recent discoveries in quantum biology suggest that biological systems might be more clever at exploiting quantum effects than previously thought. Whether or not quantum mechanics plays a direct role in consciousness, the deeper mystery remains. How does any arrangement of matter, whether classical or quantum, give rise to subjective experience? How does the objective processing of information become subjective awareness? How does the brain's representation of reality become the felt experience of being conscious? These questions push us to the very limits of scientific understanding and into territory where science, philosophy, and perhaps reflective or contemplative traditions converge. They remind us that consciousness itself might be as mysterious and fundamental as the quantum realm from which it emerges. As you breathe quietly, in whatever corner of the world has become your refuge tonight, notice the seamless flow of your own conscious experience. Thoughts arise and pass away, sensations appear and dissolve, memories surface and submerge back into the vast ocean of unconscious processing. This flowing river of awareness feels so natural, so immediate, that it's easy to forget how extraordinary it really is. You are a temporary eddy in the cosmic stream of quantum information processing, a brief organization of matter and energy that has somehow learned to experience itself. The atoms that compose your body were forged in the hearts of ancient stars through processes governed by quantum mechanics. They will eventually return to the cosmic cycle, becoming part of future stars, planets, and perhaps other conscious beings who will wonder about their place in the quantum universe. But in this moment, in this brief span between cosmic birth and cosmic return, you have the remarkable opportunity to contemplate these deepest mysteries of existence. You can wonder about the nature of reality, ask questions that push the boundaries of human understanding, and experience the profound awe that comes from confronting the fundamental mystery of being conscious in a quantum cosmos. The sense of unease we feel when contemplating the Planck scale, the vertigo that comes from realizing how much we don't know about the nature of reality, might actually be a form of cosmic homesickness. We are quantum beings trying to understand our quantum origins, temporary patterns of organization, attempting to comprehend the deeper patterns from which we arose. But perhaps the real wisdom lies not in solving these mysteries completely, but in learning to live peacefully with profound uncertainty. Perhaps the universe is not a puzzle to be solved, but a poem to be experienced, a vast work of art whose beauty lies partly in its incomprehensibility. The questions we've explored tonight about the Planck scale, quantum mechanics, and consciousness represent the growing edge of human knowledge, the frontier where scientific understanding meets the fundamental mystery of existence itself. They remind us that we are part of something far greater and stranger than our everyday experience suggests. These mysteries connect us to the deepest rhythms of cosmic evolution, to the quantum processes that gave birth to stars and galaxies, to the information processing that underlies all physical phenomena, to the extraordinary emergence of consciousness that allows the universe to contemplate itself through creatures like us. If you've been following these gentle explorations into the deepest mysteries of reality, you might find resonance in our previous journey, titled Spacetime Fabric Just Shattered, Reality is an Illusion, where we explored how Einstein's smooth continuum gives way to something far stranger at the quantum level, revealing the profound connections between consciousness, information, and the very nature of existence itself. For now, as night settles around you, and these profound questions begin to merge with the approaching realm of dreams, remember that you are not alone in this vast and mysterious cosmos. You are woven into its very fabric, composed of its deepest mysteries, blessed with the extraordinary capacity to wonder about your own miraculous existence in a universe where reality itself might be far stranger and more beautiful than we ever dared imagine. Rest well, fellow travellers in the quantum foam, and know that in contemplating these mysteries, you participate in the universe's most remarkable achievement, the emergence of consciousness from cosmic complexity, the blossoming of awareness from the quantum ground of being, the transformation of stardust into minds capable of asking why there is something rather than nothing at all. As you drift deeper into these contemplations, feeling perhaps the gentle weight of evening settling around you, consider how this fundamental uncertainty at the smallest scales might actually be the source of everything we find meaningful in existence. Without the quantum indeterminacy that emerges at the Planck scale, the universe would be a perfectly predictable machine, incapable of generating the surprises, the creativity, the very capacity for wonder that makes conscious experience possible. Some interpretations suggest, though this remains purely speculative, that consciousness itself might have evolved precisely because the universe is fundamentally uncertain. In a completely deterministic cosmos, there would be no evolutionary advantage to awareness, no benefit to subjective experience. But in a quantum universe where the future emerges from probability rather than certainty, consciousness might serve as a kind of adaptive navigator, helping complex systems respond within an inherently uncertain environment. This is not to say that consciousness directly influences quantum events, a claim that lacks scientific consensus, but rather that awareness might have emerged as nature's response to quantum uncertainty. Your ability to feel confused by these ideas, to experience wonder at the mystery of existence, to make choices in an uncertain world, all of these capacities might be gifts from the quantum realm, evolutionary adaptations to a universe where possibilities outnumber actualities. The strange loops that emerge when we contemplate consciousness, contemplating quantum mechanics, reveal something profound about the nature of self-reference in the universe. You are quantum fields, arranged in such a way that they can ask questions about quantum fields. You are uncertainty made aware of its own uncertain nature. You are the cosmos becoming conscious of its own mysterious foundations. This self-referential quality appears throughout quantum mechanics in ways that continue to puzzle physicists and philosophers. The measurement problem arises partly because we cannot cleanly separate the quantum system being measured from the measuring apparatus, which is itself composed of quantum components. Every attempt to observe quantum reality involves quantum systems observing other quantum systems, creating nested hierarchies of observation that seem to spiral into infinite regress. Some researchers have proposed that this infinite regress might actually be a feature rather than a bug, that consciousness itself might emerge from these self-referential loops in quantum information processing. This remains highly speculative and without scientific consensus, but it points toward questions about the relationship between self-awareness and physical reality that push the boundaries of both neuroscience and fundamental physics. The delayed choice experiments we discussed earlier reveal another aspect of this mystery. When future measurements seem to influence past quantum events, we encounter a universe where the normal relationship between cause and effect becomes less strictly linear rather than linear. These temporal loops in quantum mechanics might seem abstract and removed from everyday experience, but they point toward profound questions about the nature of time, causality, and free will that affect every aspect of human existence. If the quantum realm operates according to principles where future and past are more intertwined than classical physics suggests. What does that mean for our sense of agency, our feeling that we can choose our actions and influence our future? The block universe interpretation of relativity already challenges our intuitive sense of flowing time by suggesting that past, present, and future all exist simultaneously in a four-dimensional space-time continuum. Quantum mechanics adds another layer of complexity by introducing probability and measurement into this eternal structure, creating what some physicists call an evolving block universe where the future exists in potential but becomes actual through the accumulation of quantum measurements. In this view, time doesn't flow like a river, carrying us from past to future. Instead, it resembles a growing tree where new branches of reality constantly sprout from quantum measurements, each branch representing a different possible future that becomes increasingly definite as more measurements are made. Your consciousness might be following one particular branch of this cosmic tree, but countless other branches represent the paths you didn't take, the choices you didn't make, the quantum events that unfolded differently. As you breathe quietly in whatever sanctuary you found tonight, notice how even this simple act connects you to these cosmic mysteries. The oxygen molecules entering your lungs were created through nuclear fusion in stellar cores, processes governed by quantum mechanics. The chemical reactions that extract energy from these molecules and fuel your thoughts depend on quantum tunneling effects in cellular mitochondria. Even the neural processes that allow you to understand these words operate through quantum mechanical interactions between electrons in synaptic membranes. You are not separate from the quantum world. You are a temporary manifestation of it, a brief organization of quantum fields that has somehow learned to contemplate its own mysterious nature. The uncertainty that characterizes quantum mechanics flows through every aspect of your being, from the quantum fluctuations in your DNA to the probabilistic firing patterns of neurons in your brain. Recent research in quantum biology has revealed that biological systems exploit quantum effects in ways that were previously thought impossible. Photosynthesis uses quantum coherence to achieve near-perfect efficiency in energy transfer. Some birds navigate using quantum entanglement in specialized proteins. Even the sense of smell might involve quantum tunneling in olfactory receptors. These discoveries suggest that life hasn't just adapted to exist in a quantum universe, it has learned to harness quantum effects for survival advantages. Evolution appears to be a quantum process, using uncertainty and probability to explore the space of possible organisms, constantly experimenting with new arrangements of matter that might better exploit the strange properties of quantum reality. The emergence of consciousness from this quantum biological foundation remains one of the deepest mysteries in science. How do quantum processes in neurons give rise to subjective experience? How does the brain's quantum information processing become the felt sense of being aware? These questions venture into territory where neuroscience, quantum physics, and philosophy of mind converge in ways that challenge our most basic assumptions about the nature of reality and consciousness. Some researchers have proposed that consciousness might be understood as a kind of quantum field effect, emerging from the complex interactions between quantum fields in the brain. Others suggest that awareness might be a fundamental feature of certain types of information processing, regardless of whether that processing happens in biological or artificial systems. These ideas remain highly speculative and lack scientific consensus, but they point toward a view of consciousness as something more fundamental than an emergent property of classical neural computation. If consciousness is somehow connected to the quantum foundations of reality, then your awareness of these mysteries might represent a deep form of cosmic self-recognition, the universe becoming conscious of its own quantum nature through arrangements of matter complex enough to support subjective experience. The hard problem of consciousness, the question of how objective physical processes give rise to subjective experience, takes on new dimensions when viewed through the lens of quantum mechanics. Classical physics suggests a universe of pure objectivity, where subjective experience is somehow an illusion or epiphenomenon. But quantum mechanics introduces an irreducibly observer-dependent element into the heart of physics through the measurement problem and the observer effect. This doesn't mean that consciousness directly causes quantum events, a claim that remains unproven and controversial, but it does suggest that the relationship between mind and matter might be more intimate than classical science assumed. The universe revealed by quantum mechanics is not a collection of objective facts waiting to be discovered, but a web of relationships between observers and observed, between questions and answers, between potential and actual. In this quantum universe, consciousness might not be an accident or afterthought, but an integral part of how reality unfolds. The very capacity for awareness, for asking questions about existence, for experiencing wonder and confusion in the face of cosmic mystery, might be woven into the fabric of spacetime itself. As these ideas settle into the quiet spaces of your mind tonight, consider what it means to be conscious in such a universe. Every thought you think, every decision you make, every moment of awareness you experience represents a unique perspective on reality that has never existed before and will never exist again. You are not just observing the universe, you are participating in its ongoing unfolding, adding your own thread to the vast tapestry of cosmic consciousness. The quantum foam that bubbles at the Planck scale, the virtual particles that pop in and out of existence, the wave functions that collapse when measured, all of these might be aspects of a deeper reality where mind and matter, subject and object, observer and observed are different facets of a more fundamental unity. This unity doesn't erase the distinction between self and world, but suggests that the boundary between them might be more permeable than everyday experience indicates. The atoms that compose your body exchange constantly with your environment. The thoughts in your mind emerge from processes that extend far beyond the boundaries of your skull. The very sense of being a separate self might be a useful model that emerges from deeper patterns of connection and relationship. If you enjoy drifting through these explorations of consciousness and cosmos without interruption, members of our community get every episode 48 hours early, completely ad-free, allowing for uninterrupted contemplation of these profound mysteries. You can join them whenever you feel ready to dive deeper into these questions that sit at the intersection of science and wonder. The anthropic principle adds another layer of mystery to our understanding of consciousness and quantum mechanics. The fundamental constants of nature appear to be fine-tuned for the existence of complex structures like stars, planets, and life with extraordinary precision. This fine-tuning might be explained by the multiverse hypothesis, suggesting that we observe these particular values because we couldn't exist in universes with different constants. But this raises profound questions about the relationship between consciousness and the fundamental structure of reality. If the universe must be capable of producing observers in order for anyone to observe it, then consciousness might play a more central role in cosmic evolution than we typically assume. Not because conscious minds directly influence physical events, which remains unproven, but because the very possibility of consciousness might constrain the kinds of universes that can exist. Some interpretations suggest, though this remains purely speculative, that consciousness and the physical universe might have co-evolved, each shaping the other through processes we're only beginning to understand. The universe develops the capacity to support conscious observers, and conscious observers develop the capacity to understand the universe, creating feedback loops that might drive both cosmic and cognitive evolution. This co-evolution might explain why mathematical concepts discovered through pure thought often turn out to describe physical reality with uncanny accuracy. The same quantum processes that govern the behavior of particles might also govern the neural processes that generate mathematical insights, creating deep connections between the structure of mind and the structure of reality. The unreasonable effectiveness of mathematics in describing nature, as physicist Eugene Wigner called it, might not be so unreasonable if both mathematics and nature emerge from the same quantum informational foundations. Your ability to understand these concepts, to follow abstract mathematical arguments, to grasp the connections between seemingly unrelated phenomena, might reflect deep structural similarities between the patterns in your mind and the patterns in the cosmos. Recent developments in quantum information theory have revealed that information might be more fundamental than matter or energy. The IT from bit hypothesis suggests that physical reality emerges from binary questions and answers at the quantum level, that every particle, every field, every force might be made of information rather than substance. If this interpretation is correct, then consciousness might not be something that emerges from complex arrangements of matter, but something more closely related to the information processing that underlies all physical phenomena. Your thoughts, memories, and experiences might be patterns of information that are continuous with the informational patterns that constitute atoms, stars, and galaxies. This doesn't diminish the reality of consciousness, but suggests that it might be more fundamental than we typically assume. Instead of being a late addition to a universe composed primarily of unconscious matter, consciousness might be present in some form at every level of reality, from quantum fields to cosmic structures, manifesting most clearly in complex systems like brains, but never entirely absent from any informational process. The integrated information theory of consciousness proposes that any system that integrates information possesses some degree of consciousness, however minimal. If this theory is correct, then consciousness might exist at every scale of the universe, from elementary particles to planets, with human awareness representing just one particularly complex manifestation of a more universal phenomenon. This panpsychist interpretation remains highly controversial and lacks scientific consensus, but it offers a potential resolution to the hard problem of consciousness by suggesting that subjective experience is a fundamental feature of reality rather than an emergent property of complex systems. It transforms the question from how does consciousness arise from unconscious matter to how does simple consciousness become complex consciousness? As you sit quietly contemplating these possibilities, notice how the boundary between your inner experience and the outer world becomes less distinct. The thoughts arising in your mind emerge from neural processes that depend on quantum mechanics. The light entering your eyes carries information that has travelled across vast distances, connecting you to stars and galaxies through electromagnetic radiation. Even the sense of being a separate self might be a pattern that emerges from deeper currents of connection and relationship. The quantum entanglement that links particles across vast distances might serve as a metaphor, though not a literal description, for the deep interconnectedness that characterizes all aspects of reality. While there's no scientific evidence that consciousness can directly create entanglement or influence distant events through thought alone, the phenomenon of entanglement does reveal that the universe is far more interconnected than classical physics suggested. This interconnectedness extends to consciousness itself. The thoughts you're thinking right now emerged from a vast network of influences. The words you're hearing, the memories they trigger, the cultural context that shape their meaning, the biological processes that support neural activity, and ultimately the cosmic history that created the elements composing your brain. You are not an isolated island of consciousness, but a node in a vast network of relationships that extends from the quantum realm to the cosmic scale. Your awareness of these mysteries represents a unique perspective on reality that enriches the universe's understanding of itself, adding your particular pattern of questions and insights to the ongoing conversation between mind and cosmos. The delayed choice quantum eraser experiments reveal that this conversation might be even more mysterious than we typically assume. When future measurements seem to influence past quantum events, we encounter suggestions that the normal relationship between cause and effect might be more fluid than classical physics indicates. While these experiments don't prove that consciousness can influence past events, they do reveal that the universe operates according to principles that transcend our everyday understanding of time and causality. They point toward a reality where past, present, and future might be more intertwined than linear thinking suggests. Some interpretations propose that consciousness itself might have temporal extension, that your awareness in this moment might somehow be connected to past and future states of consciousness in ways that transcend the normal flow of time. This remains purely speculative and without scientific support, but it points toward questions about the nature of temporal experience that challenge our most basic assumptions about the relationship between mind and time. The block universe interpretation of relativity suggests that all moments in time exist simultaneously in a four-dimensional space-time continuum. Your birth, your current experience, and your eventual death all exist eternally as different locations in this temporal landscape. Quantum mechanics adds complexity by introducing probability and measurement, but some interpretations suggest that even quantum events might exist in a kind of eternal superposition, with measurements selecting which branch of reality we experience rather than creating new realities. If this interpretation is correct, then your consciousness might not be moving through time like a passenger on a train, but rather illuminating different moments in an eternal structure like a searchlight scanning a vast landscape. Your sense of temporal flow of moments following each other in sequence might be a feature of consciousness rather than a feature of time itself. These ideas venture far beyond what current science can prove or disprove, but they illustrate how quantum mechanics and relativity together challenge our most fundamental assumptions about the nature of time, consciousness, and reality. They invite us to consider possibilities that stretch the boundaries of human understanding while remaining grounded in mathematical frameworks that describe physical phenomena with extraordinary accuracy. As the night deepens around you and these concepts begin to merge with the approaching realm of dreams, consider how remarkable it is that arrangements of quantum fields can contemplate their own nature. The universe has organized itself in such a way that parts of it can wonder about the whole, that temporary patterns of matter and energy can ask eternal questions about existence, meaning, and mystery. You are simultaneously insignificant and cosmic, a brief flicker in the vast history of the universe, and also its most remarkable achievement. Through your consciousness, the cosmos becomes aware of its own beauty, its own mystery, its own unfathomable depth. Your capacity for wonder, confusion, and awe represents the universe's ongoing attempt to understand itself through finite minds, capable of engaging with infinite questions. The sense of unease we feel when confronting the Planck scale, the vertigo that comes from realizing how much we don't know about reality, might actually be a form of cosmic homesickness. We are quantum beings trying to understand our quantum origins, patterns of organization, attempting to comprehend the deeper patterns from which we arose. But perhaps the real wisdom lies not in solving these mysteries completely, but in learning to live peacefully, with profound uncertainty, to find meaning and beauty in questions that may never be fully answered. The universe might not be a puzzle to be solved, but a poem to be experienced, a vast work of art whose beauty lies partly in its incomprehensibility. The questions we've explored tonight represent the growing edge of human knowledge, the frontier where scientific understanding meets fundamental mystery. They remind us that reality is deeper, stranger, and more wonderful than our everyday experience suggests, that we are part of something far greater than ourselves, while also being integral to its ongoing unfoldment. These mysteries connect us to the deepest rhythms of cosmic evolution, to the quantum processes that gave birth to stars and galaxies, to the information processing that underlies all physical phenomena, to the extraordinary emergence of consciousness that allows the universe to contemplate itself through creatures like us. Every breath you take, every thought you think, every moment of awareness you experience represents a unique contribution to this cosmic conversation. You are not just witnessing these mysteries, you're participating in them, adding your own pattern of questions and insights to the universe's growing understanding of itself. The Planck scale represents both a boundary and an invitation, a limit to what we can know directly and an opening to what we can imagine, wonder about, and contemplate. It reminds us that mystery is not the enemy of understanding, but its deepest source. That the questions we cannot answer might be more important than the ones we can. As you prepare to drift into sleep, or simply sit quietly with these profound uncertainties, remember that you are woven into the very fabric of these mysteries. The quantum fields that foam and fluctuate at the smallest scales flow through every aspect of your being, connecting you intimately to the deepest questions of existence. In contemplating the Planck scale and its implications for consciousness and reality, you participate in the universe's most remarkable achievement, the emergence of awareness from cosmic complexity, the blossoming of consciousness from quantum foundations, the transformation of stardust into minds capable of asking why there is something rather than nothing at all. If you found yourself drawn to these explorations of the deepest mysteries of reality, you might discover even more profound questions in our previous journey titled Spacetime Fabric Just Shattered. Reality is an illusion, where we explored how Einstein's smooth continuum gives way to something far stranger at the quantum level, revealing the intricate dance between consciousness, information, and the very nature of existence itself. Rest well, fellow travellers, in the quantum foam, and know that in wondering about these mysteries, you embody the universe's endless capacity for self-discovery, its eternal quest to understand its own magnificent, awe-inspiring, and utterly mysterious nature. The unease at the Planck scale isn't just about what we don't know, It's about the possibility that knowledge itself has limits built into the architecture of reality. As you settle into whatever quiet corner of the world has become your refuge tonight, consider this final unsettling thought. We might be living in a universe that has evolved its own mechanisms to prevent complete understanding, not as a cosmic joke, but as a necessary condition for the existence of consciousness itself. Recent investigations into what physicists call the firewall paradox reveal another layer of this intellectual puzzle. When matter falls into a black hole, quantum mechanics suggests that information about that matter must somehow be preserved, even as it disappears beyond the event horizon. But this preservation might require the formation of a firewall at the horizon, a boundary of extremely energetic effects that would overwhelm anything attempting to cross. This creates a profound puzzle about the nature of information in the universe. If information cannot be destroyed, as quantum mechanics suggests, then what happens to the information encoded in your thoughts, your memories, your entire conscious experience when your brain eventually stops functioning? Some interpretations propose that this information might somehow persist in the quantum structure of space-time itself, woven into the fabric of reality in ways we cannot directly observe, but that remain part of the universe's long-term informational structure. The implications stretch beyond individual consciousness to the nature of existence itself. If information is truly conserved at the quantum level, then every moment of awareness you experience, every question you ask about these mysteries, every fleeting thought that passes through your mind tonight, all of this becomes part of the universe's ongoing informational record, never truly lost, but transformed into patterns too subtle for us to detect. This informational view of consciousness connects to emerging theories about the nature of time itself at the quantum level. Some interpretations suggest that the flow of time might not be fundamental, but might instead emerge from the accumulation of information in quantum systems. In this view, your experience of temporal flow, of moments following each other in sequence, might be generated by the constant processing of quantum information in your brain. If this interpretation has merit, then consciousness might not exist within time, but might instead be one of the mechanisms through which time emerges from more fundamental quantum processes. Your awareness of these ideas represents the universe organizing temporal experience through the very act of processing information about itself. The present moment you're experiencing right now might be the quantum information content of reality organizing itself into patterns complex enough to generate a subjective experience. The Wheeler-DeWitt equation, which attempts to describe quantum gravity, reveals just how radical this reimagining of time might be. In the fundamental equations that govern the deepest level of reality, time appears to vanish entirely, leaving behind a static description of all possible configurations of the universe existing simultaneously in what physicists call Wheeler superspace. From this perspective, your entire life, from birth to death, might exist as a single static pattern in this timeless quantum landscape. What you experience as the flow of time, the succession of moments that creates the narrative of your existence, might be a kind of internal navigation through this eternal structure, a way that consciousness moves through the static geometry of all possible realities. This doesn't diminish the reality of your temporal experience, but suggests that it might be more mysterious and more fundamental than classical physics assumed. Time might not be the stage upon which consciousness performs, but rather one of the phenomena that consciousness helps organize through its very existence. Take a moment to breathe deeply and notice how this breathing connects you to these temporal mysteries. Each breath represents a cycle of exchange with your environment, atoms entering and leaving your body, quantum processes in your cells, extracting energy from molecules that were once part of ancient stars. Even this simple act of breathing involves you in the cosmic circulation of matter and energy that has been flowing for billions of years. The quantum field fluctuations that occur in every cubic centimetre of space around you are constantly creating and dissolving virtual particles in time frames so brief that they challenge the very concept of duration. These quantum events occur in what physicists call proper time, a kind of internal clock that each quantum system carries with it, independent of the coordinate time we use to organise daily life. Your consciousness emerges from neural processes that operate according to their own proper time, quantum events in synaptic membranes, and cellular structures that create the rhythms of thought and awareness. The time you experience subjectively might be quite different from the coordinate time measured by clocks, shaped instead by the internal dynamics of quantum information processing in your brain. Recent research in chronobiology has revealed that biological systems maintain their own internal clocks that can diverge significantly from external time standards. These circadian rhythms emerge from quantum processes in cellular mechanisms that have evolved to track cycles of day and night, seasonal changes, and subtle environmental cues. But these biological clocks represent just one layer of temporal experience. Deeper still are the quantum mechanical processes that occur in timescales measured in femtoseconds and attoseconds, far below conscious awareness, but fundamental to the chemistry of life. The quantum tunneling events that allow enzymes to catalyze biochemical reactions occur in time frames so brief that they exist in a realm where the normal relationship between cause and effect becomes less intuitive. Some interpretations of quantum mechanics suggest that these ultra-fast quantum events might not occur within time as we normally conceive it, but might instead be processes that give rise to the appearance of temporal flow through their collective behaviour. If this interpretation has merit, then the deepest processes that sustain your life and consciousness might operate in regimes where past, present, and future lose their usual meaning. The quantum Zeno effect reveals another way in which observation and time become intertwined in quantum systems. When quantum systems are observed continuously, their evolution can be slowed or altered by the act of measurement itself. This suggests that awareness and time might be more intimately connected than classical physics assumed. While this does not mean that consciousness directly controls time, a claim that would lack scientific support, it does suggest that the relationship between awareness and temporal flow may be more subtle and complex than we typically assume. Your conscious attention to these ideas, your ability to hold concepts in working memory and compare them to prior experiences, may represent a unique form of temporal organisation emerging from neural dynamics. The measurement problem in quantum mechanics becomes even more mysterious when we consider its temporal aspects. When a quantum superposition resolves into a definite outcome, this transition appears instantaneous relative to normal time descriptions. But what determines when this transition occurs? How does the universe determine the moment when possibility becomes actuality? Some interpretations suggest that consciousness might play a role in these transitions, though this remains speculative and lacks scientific consensus. The delayed choice experiments we discussed earlier hint at even stranger possibilities, suggesting that future measurements may be correlated with earlier quantum outcomes. So here we find ourselves at the edge of understanding having explored realms so small that they challenge the meaning of existence itself. We've descended through the layers of reality, past everything we can see or touch, past atoms and quarks, to a place where familiar concepts of space and time begin to soften and dissolve. The Planck length represents more than just an incredibly tiny distance. It marks the boundary where our most successful theories of physics reach their limits, where the universe seems to have hidden its deepest workings behind barriers that may be unreachable in principle. At these smallest scales, reality may be fundamentally uncertain, constantly fluctuating in patterns we can model mathematically, but never observe directly. Perhaps most unsettling of all, we've seen how this limitation may not be temporary, but structural. The very act of attempting to probe the Planck scale would overwhelm both observer and observed, as if reality has evolved its own constraints to protect its most intimate processes. Yet in contemplating these mysteries, we've also discovered something beautiful. You are not separate from these quantum uncertainties, but deeply woven into them. Every atom in your body, every thought in your mind, every moment of awareness emerges from processes that ultimately touch these deepest layers of reality. The uncertainty that unsettles us at the Planck scale is the same uncertainty that makes growth, creativity, and wonder possible. Sleep well tonight, knowing that you are part of something far more mysterious and magnificent than everyday experience suggests. And remember, sometimes the most profound wisdom lies not in finding all the answers, but in learning to rest peacefully with the most beautiful questions.